Here we have a direct application of central percussion concept. This is actually a laboratory test equipment that exists. What is being tried here is to have this pendulum swing from a distance. So it's going to have some potential energy that's going to be converted to kinetic energy until it hits the specimen. And as it hits the specimen, its acceleration drops suddenly to zero, releasing all the energy and transferring it to the specimen. And you're testing the specimen if it's going to break or not. And what you don't want in the system is your laboratory equipment to break. Where it's going to break or where it's going to be damaged is mostly this revolute joint location. It will have this reaction forces due to the impact. And if you want to minimize these reaction forces, even make it equal to zero, then you would want to design this pendulum in such a way that the location that it hits the specimen is actually the center of percussion, which will result in zero reaction force due to the impact. There will be a reaction force due to the motion. However, due to the impact, the reaction force will be equal to zero if you can design it in this way. So this is that design question. It's asking us where the center of percussion should be. It's located b distance away from the mass center. And what is given to us is that this pendulum is 34 kilograms. It has a radius of gyration above 0.0. So what's given us is this kappa O information. Is 620 millimeters. And then we could find this Q by using this kappa O information actually. And the mass center's location with respect to O is given. So R information is already available to us. So if we take a look back here, kappa O squared over RG would give us this Q information, which is going to be equal to 600 millimeters plus B. So we have that information. We can design this B. But then there is another part to that question. After we calculate this B, we are asked to calculate the magnitude of the total force R. This is the reaction force at the bearing at O, an instant after the release from theta equals to 60 degrees. So theta is equal to 60 degrees. The release happens, and at that instant, what is going to be this R? So we need to calculate at that instant what are the acceleration values in this direction and in that direction, right? There will be tangential direction, normal direction. Remember that normal direction is calculated by omega squared R. At the instant when it is released, omega is actually equal to zero. So the motion along the acceleration along the normal direction will be equal to zero. There will be acceleration in the tangential direction at the time of the release, just after the release. However, there's an easier method to do that calculation to find the reaction force. We can actually call this point Q the center of percussion, and then we would remember that the summation of the moments about the center of percussion is equal to zero. So summation of moments about the center of percussion is equal to zero. So this is yet another way to find out the reaction forces. So basically we're going to use again the Newton's equation and the moment equation. But this is these are the information given to us in this question, a fixed axis rotation question. So impact force, when it hits the specimen at this location, impact force is in that direction, and then it's not going to affect the Rn. RT will be affected. However, if we use it as a center of percussion, this location where it hits, if we design it in that way, then this RT will be equal to zero as a result of this impact. And again, we use our equation here, which is already derived for us, so we don't need to derive it again. There is this Q equals to kappa squared over RG. kappa is given to us, Rg is given to us, and then Q, we know that it's 600 millimeters or 0.6 meters plus B distance away, so B can be found easily from this equation. Now the next part is about the calculation of the reaction forces at this instant, not at this instant where it hits the specimen, just after the release. Just after the release, we can write two equations, summation of forces in the tangential direction, summation of forces in the normal direction. Now, in the tangential direction and normal direction, what else we have is the mass times the gravitational force we have, and it's going to have a component in the normal direction, it's going to have a component in the tangential direction, and as we know the angle theta, we can calculate that. The tangential direction force will be mg times sine 60 degrees, and the normal component is mg times cosine 60 degrees. You need to be careful about the directions. If we consider this is the normal direction, this is the positive direction, then it will be negative mg times cosine 60 degrees in the normal direction. And then on the right hand side of the equation, we will be able to write out the m times an and m times at. What we know about an at that instant is omega is equal to 0 at that instant, so an goes to 0. So for this part of the equation, for this part of the scalar part of the Newton's equation, we get a 0 on the right hand side. For ft, we have 80, but we don't know it. Can we calculate that? Yes, we can. First of all, we need to work out the equation for mo and then IO times alpha, and then we need to calculate alpha from here. Then we will use this alpha to calculate the tangential acceleration, which is going to be r times alpha, and then we can substitute that here, and that will be a solution. Okay, that's a way to find the solution. But the other way of finding the solution is we can write out the summation of moments about Q, and we already know that at the center of percussion, the summation of moments will be equal to 0. What forces we have here is the gravitational force and the tangential reaction force, RT. We have RT here, and then a component of mg, and the component is in the tangential direction. The normal direction components of the reaction force and mg do not generate any moment about point Q, because point Q is along the line of OG. Okay, so keeping that in mind, we can write this equation that the summation of moments about Q is equal to 0. There we have this mg component, the sine component. This is the component. Okay, that's our component here. Mg component, mg sine 60 degrees, and the distance is to the center of percussion, which is the B we calculated over here, 0.0407. That's our distance to the center of percussion. Then from RT to Q, the distance is 600 plus 0.407, or 0.6 plus 0.0407. And we have a negative sign due to the selection of our direction. We selected the direction in this way, so we are not contrasting with our or contradicting with our selection of the arrow here. This arrow will generate, this force will generate the moment in the clockwise direction. The gravitational force, however, will generate a moment in the counterclockwise direction. So that's why there has to be a minus sign here. You either put the minus sign here, or you say plus here and then minus here, whichever way you like. Actually, it will be the same. But using the right hand rule, the moment generated by mg would be a plus, then the moment generated by this reaction force would be a minus. Again, this is based on the direction that you choose. We could have chosen this direction, by the way, and then it will be a plus, but then we will get a minus sign for RT. And minus sign would mean that the correct direction is the direction that is shown here with the black arrow. So we calculate this RT from here. From the Fn equation on the right hand side, we know that this has to be 0 because at the instant of release, just after the release, omega g is equal to 0. So we have Rn and then a component of the gravitational force acting in that direction where we can calculate Rn, and then finally we can find the total reaction force. Again, the other way that you can tackle this problem is by using this moment equation about point O, calculate alpha, use that alpha to calculate the acceleration at the mass center, and then work out the equation about the tangential component of the force equation of Newton.